All right, let's dive in. We've got these fascinating sources you sent over, and they're all pointing towards something, well, potentially game-changing for powering transport,
Yeah.
the big stuff.
Exactly. Yeah, think about the really heavy hitters, airplanes, ships, long-haul trains. Electrifying those, the huge hurdle is always energy storage. Batteries, the lithium-ion ones we have in cars, great, but just too heavy for the energy they pack for these massive applications.
Right, weight is everything,
Yeah.
especially
Yeah.
when you're trying to get off the ground. So these sources dig into this idea, mainly from MIT, that kind of sidesteps the whole battery issue. It's not a battery at all, is it?
No, it's being framed as a fuel cell, and the key difference there is refueling. Batteries take ages to recharge, right? This system is designed so you can swap the fuel out quickly.
And the fuel is, okay, get this, liquid sodium metal, which sounds maybe a bit intense.
It does sound a bit out there. And the lead researcher, Yet Ming Chang, he actually said, according to the sources, something like, "We expect people to think this is totally crazy." He'd apparently be disappointed if they didn't think it was crazy because, revolutionary ideas often sound nuts at first.
Huh. Fair point. So the science here suggests it might actually be revolutionary. That's what we're digging into today, right? Why this liquid sodium thing could be the breakthrough for electrifying heavy transport.
Exactly. Let's unpack why it's potentially such a big deal.
Okay, so starting with the problem. Batteries are too heavy. How heavy is too heavy? What are the numbers the sources give us?
Well, the key metric is energy density. How much energy per kilogram? Lithium ion, like in your EV, tops out around 300 watt hours per kilogram. Maybe a bit more now, but that's the ballpark.
300 West kilograms.
Okay.
And for planes, what's the magic number we need to hit?
The researchers are targeting about 1,000 West kilograms. That's seen as the threshold for making electric aviation realistic, at least initially.
1,000. Wow. Okay. That's more than triple what we have now. So if we hit 1,000, are we talking electric 747s crossing the Atlantic?
No, not quite there yet. The sources are pretty clear. Transcontinental, transatlantic flights, those are still really far off for, well, any known chemistry. But 1,000 which key is enough for regional electric aviation.
Regional flights.
Mm-hmm.
But that's still a massive chunk of air travel, isn't it?
Oh, absolutely huge. Regional routes make up something like 80% of domestic flights in places like the U.S., and they account for, maybe 30% of total aviation emissions. So tackling that's a really significant win.
Okay, so 1,000 which key gets us regional planes. You mentioned ships and trains, too. They need this density as well.
Yeah, they do. Maybe not quite as weight critical as planes, but for long-range shipping or powerful trains, you still need a ton of energy without taking up all the space or costing a fortune. High energy density helps everywhere, basically. Current batteries struggle there, too.
Got it. So the need is clear. Enter the crazy sodium fuel cell. How does it actually work? Can you break down the basic setup from the sources?
Sure. It's actually elegantly simple at its core. You've got liquid sodium metal on one side.
The fuel.
Right, the fuel. On the other side, just air.
Just air, like normal air.
Yep, just plain old air. That provides the oxygen for the reaction. And in between them, there's this solid ceramic material. That's the electrolyte. And it's special because it lets sodium ions pass through, but not electrons or anything else.
Okay, so liquid sodium, a ceramic separator, and air. Where does the electricity come from?
There's a porous electrode on the air side. It basically helps the sodium ions coming through the ceramic meet the oxygen from the air. When they react, boom, that chemical reaction generates electricity.
Now, the sources mentioned this idea, metal-air energy, isn't brand new. We've heard buzz about lithium air or sodium air before, yeah.
Oh yeah, for decades. People have known the theoretical energy density is massive. The sources say for like 30 years, way higher than conventional batteries.
So if the potential is so high, why aren't these things everywhere already? What's been the holdup?
The big problem has always been making them rechargeable reliably. Trying to reverse that metal-air chemistry inside the cell over and over.
Right.
It tends to degrade things, cause side reactions, sometimes safety issues. It's just tricky.
Oh.
So what this MIT team did was kind of pivot. They said, okay, forget recharging for now. Let's make it a fuel cell, get the energy density benefit, but instead of recharging, you just swap out the used fuel for fresh fuel.
Right, refueling instead of recharging. That makes a lot of sense.
Right.
Okay, let's get to the really exciting part. The performance numbers they're actually seeing in the lab.
This is where it gets really impressive. In their prototype cells, the sources say they measured energy densities approaching 1,700 watt-hours per kilogram. That's at the cell or stack level.
Hold on, 1,700. The target for planes was 1,000. They didn't just meet it, they smashed right past it.
They really did. And even when they project it out to a full system, including pumps, heating, all the supporting bits, they still expect it to be over 1,000 weighting milligrams. That's the key. It's not just a little better. It's potentially, like the sources say, revolutionary, more than 3 times current lithium ion.
Yeah, that is a massive leap. But density isn't everything. What about cost, availability? Lithium and cobalt have issues there.
Another huge plus. Sodium comes from sodium chloride. Salt. Common table salt. It's everywhere, super abundant, easy to get. So the fuel itself is potentially dirt cheap compared to lithium, cobalt, nickel, all those materials with complex supply chains and, frankly, geopolitical baggage.
Abundant, cheap global supply.
Yeah.
Okay, that sounds almost too good. But handling pure sodium metal, isn't that tricky? The sources mentioned we've done it before.
Yeah, surprisingly, there's a precedent. Back when lead was added to gasoline tetrethyl lead, making it required huge amounts of sodium metal, the U.S. alone was apparently producing 200,000 tons a year.
Wow.
So while you absolutely have to be careful handling it, the point is industry knows how to produce and manage metallic sodium safely at a very large scale. It's not some unknown quantity.
Okay, that's reassuring. So high density, cheap fuel, we know how to make it. How does the refueling actually work? For a plane, say.
The vision described is pretty neat. Think refillable cartridges or packs filled with the liquid sodium. When one's used up, you just pop it out and slide a fresh one in. The sources use this analogy I liked, like swapping out racks of food trays in a cafeteria. Quick and easy.
Racks of food trays, I can picture that. But liquid sodium, doesn't that mean it has to be incredibly hot?
Not crazy hot, no. Sodium actually melts at 98 degrees Celsius. That's just under boiling water temperature. So, yeah, you need to keep it warm, but it's a manageable temperature, making it relatively easy to keep liquid for swapping those cartridges.
Okay, just needs to be kept warm, not molten lava hot. Got it. This all sounds amazing. But hitting 1,700 wiki drains when others struggled.
Yeah.
What was the breakthrough? What did these researchers figure out?
According to the sources, a really crucial insight came from understanding the role of humidity. Specifically, one of the PhD students, Karen Sugano, really dug into this.
Humidity in the air going into the cell. That seems like such a tiny detail for such a huge result.
Doesn't it? But it was apparently absolutely critical. They found that if you carefully control the amount of moisture in the air flowing through, the performance just skyrockets.
Okay, why? What does the moisture do?
Well, the problem with the dry air, it turns out, is that the reaction product, sodium oxide, forms as a solid. And this solid stuff just clogs up the electrode surfaces, blocks the reaction. It basically grinds the whole process to a halt. That's been a major issue for metal air concepts before.
The solid gunk problem.
Exactly. But with the right amount of humidity, the sodium reacts to form its discharge products in a liquid form instead. And that liquid can just be easily swept away by the airflow.
So the liquid doesn't build up and block things like the solid does. You just flush it out.
Precisely. Forming that liquid product and getting rid of it easily, that, the sources say, was the key insight that led to the big bump in performance.
That's really cool, solving a major roadblock with something as basic as managing humidity. The sources also mentioned they weren't just fuel cell people, right? They pulled from different areas.
Yeah, it sounds like a classic interdisciplinary success story. They drew on knowledge from older, high-temperature battery research people, looked at sodium batteries way back, and also from the newer sort of niche field of sodium-air batteries plus fuel cell design.
Kind of mixing and matching the best bits.
Pretty much mushing it all together, as one quote put it. That combination of perspectives plus the humidity discovery seems to be what unlocked this level of performance.
Okay, so if you're reacting sodium with air, what actually comes out? Is there like an exhaust pipe? Does it produce CO2?
There'd be an exhaust stream, yeah, carrying away that byproduct. But here's maybe the most mind-blowing part highlighted in the sources. 0 carbon dioxide emissions from the fuel cell operation itself.
No CO2. That alone is huge for transportation. So what is the byproduct then? You said sodium oxide initially.
Right, sodium oxide is the first thing formed. But then the sources describe this amazing natural cascade of reactions that happens spontaneously as soon as that sodium oxide hits moisture in the outside air.
A natural cascade. Okay, tell me more. What happens?
So the sodium oxide instantly reacts with water vapor, just moisture in the air, to form sodium hydroxide. You might know that better as lye, or a main ingredient in drain cleaner.
Right, okay, so drain cleaner is the exhaust. Still doesn't sound great.
But wait, here's the brilliant part. Sodium hydroxide is incredibly good at grabbing carbon dioxide. So as this stuff flows out, it just naturally sucks CO2 right out of the surrounding atmosphere.
It pulls CO2 out of the air.
Yes, it reacts with the atmospheric CO2 to form sodium carbonate first, and then that quickly becomes sodium bicarbonate.
Sodium bicarbonate. Wait,
Yep.
isn't that just baking soda?
Exactly, baking soda. So the whole process effectively turns the initial sodium oxide byproduct into harmless baking soda by actively removing CO2 from the air. And it just happens.
Right.
No extra energy needed, no special scrubbing equipment. It's a passive, built-in carbon capture.
So this thing isn't just carbon neutral, it's actually carbon negative. It cleans the air while it makes power.
That's what the science presented strongly suggests, yeah. The byproduct reaction consumes atmospheric CO2. And the sources make a great point. People have looked at using sodium hydroxide for industrial carbon capture before, but it's usually way too expensive because making the sodium hydroxide costs a lot.
But here it's just free. A
Yeah,
side effect of making electricity.
exactly. You get this potentially massive environmental bonus actively scrubbing CO2 basically for free as part of the process. And there's even a mention that if this sodium bicarbonate ends up in the ocean, it could help counteract ocean acidification, another big climate change problem.
Wow. Okay, that is genuinely astonishing. Powering planes and cleaning the air. It does sound almost too good. Which makes me ask about safety. Sodium metal, water. That,
Yeah.
that's famously reactive, right?
Absolutely. Safety is a huge factor, and the sources address it. Sodium metal is highly reactive, no question. You have to contain it properly, protect it from air and moisture, much like lithium in batteries, actually. It can ignite if exposed.
And with these super high energy densities, if something
Yeah.
goes wrong, like the barrier inside fails,
Yeah.
is there a risk of, a runaway reaction?
That's definitely a concern with some battery designs where you have two very potent chemical reactants packed right next to each other. But the researchers argue this fuel cell setup is inherently safer in that specific failure scenario.
How so? Why safer?
Because on one side, you have the concentrated fuel, the sodium, but on the other side, it's just air. Air is mostly nitrogen, the oxygen is dilute, it's not another highly concentrated reactant. So if that ceramic membrane cracks or fails,
The reaction wouldn't be as violent.
exactly. The potential for a massive, uncontrolled energy release is thought to be much lower compared to having two highly reactive materials suddenly mix. They believe pushing for this kind of energy density is actually safer in a fuel cell format than trying to cram it all into a traditional battery structure.
That makes sense. Diluting one side of the reaction lowers the immediate risk. Okay, so where is this technology right now? Is it about to go into production?
Not quite yet. What they have now is a small proof of concept, single cell prototype working in the lab.
Okay, so definitely still early stages. But what's the plan? The path forward?
They seem confident it's scalable. Some of the researchers have already spun out a company called Propel Aero. It's based in MIT's incubator, the Engine, aiming specifically to commercialize this tech.
Propel Aero. Good name. What's their first target?
The near-term goal, like within the next year or so, is to build a bigger working unit about the size of a brick. This would be designed to produce around 1,000 watt-hours of energy, enough to actually power something real, like maybe a large drone used for agriculture.
Ah, practical demonstration. Prove it works outside the lab.
Exactly. Show it functions reliably in a tangible application. And then the longer-term vision is obviously scaling up much further, developing the bigger systems, proving the durability, the safety at scale, everything needed for aircraft, ships, and trains.
Okay, let's pull this all together then. Based on these sources, what are the absolute key takeaways you see for this liquid sodium fuel cell idea?
Well, first, the energy density is potentially revolutionary, hitting and even exceeding that 1,000 West Keob target needed for regional electric flight. That's huge, way beyond current batteries.
And the fuel source, sodium from salt, is incredibly attractive. Cheap, abundant, globally available, avoids those tricky battery material supply chains, and we even have historical proof we can handle it at scale.
Right. Plus, the refueling concept seems practical, just swapping cartridges of liquid sodium, which melts at a pretty manageable temperature just below boiling water.
And then there's that absolutely wild potential environmental benefit. The byproduct spontaneously reacting to pull CO2 out of the atmosphere, turning into baking soda. Essentially free carbon capture built in.
Yeah, that's amazing. And while safety with sodium is crucial, the fuel cell design itself might offer inherent advantages over some battery types when you're packing in this much energy, because one side is just dilute air.
And finally, while it's early days, just a lab prototype, now there's a dedicated company, Propel Aero, with a clear roadmap. Build a demonstrator unit soon, and then aim for those big, heavy transport applications.
It really could be the key to unlocking electrification for sectors that just seemed out of reach for batteries alone, starting with those regional planes.
It definitely makes you think differently, doesn't it? Imagine a future where our planes and ships aren't just getting us from A to B, but are actively helping to clean the air while they do it.
It really does, and it leaves you wondering, what other everyday systems or processes might have these kinds of hidden beneficial side effects, these surprising environmental bonuses just waiting to be discovered, like this fuel cell potentially scrubbing CO2?
That's a great thought to chew on. Thanks for walking us through this incredible potential breakthrough on the deep dive.